In this chapter, I will discuss the nature of light. In the previous two chapters, we learned a great deal about light by simply observing how it behaves, but we did not ask what is light. And this question is easy to ask, but the answer is not very easy to give. And the reason for that is that we cannot see light. We only sense the stimulation caused by light entering our eyes, but we do not see light itself. To understand what light is, we need to look for analogies to ask ourselves what things behave like light. In effect, we are building a model of a phenomenon that we can't observe directly. This same problem occurs quite often in physics because many components of nature are not directly observable. In the case of light, we need a model that accounts for the properties that we studied in the previous two chapters. When we look at the world around us, we see that there are two candidates, either particles or waves. So then the question becomes, does light behave as if it were a stream of particles or series of waves? And historically, Newton thought that light was a stream of particles, but other prominent scientists of his time thought that it behaved like waves. So because of Newton's great reputation, his particle model of light was the accepted theory during the 18th century. However, many of the early observations could be explained by a particle model or a wave model. So scientists continually looked for new observations and that could distinguish between the two theories. So we will examine the experimental evidence to see whether light behaves like particles or waves. The first phenomenon to look at is reflection. We know from such common experiences as echoes and billiard balls that both waves and particles can bounce off barriers. But this fact is not enough to determine whether light is of particle-like nature or wave-like nature. Our model for the behavior of light must agree with our conclusion that the angle of reflection is equal to the angle of incidence. As you remember, when we talked about reflection, the law of reflection stated that the angle of incidence is equal to the angle of reflection. A particle model for light can account for this if the reflecting surface is frictionless and perfectly elastic. Imagine you're bouncing a perfectly rigid sphere, let's say made from stainless steel, off of a really thick stainless steel surface. This ensures that there are practically no deformations of the two objects, the sphere and the surface. And let's make sure that there is no friction between the sphere and the surface. For example, we can coat both with a thin coat of very small viscosity oil. So when those conditions are met, the ball will bounce off this surface at an angle of reflection equal to the angle of incidence. That is because the collision between the sphere and the surface will be a perfectly elastic collision without loss of any energy. Of course, this experiment also must be done in vacuum so that there is no generation of sound waves. On the other hand, a wave model of light also has no problem accounting for the law of reflection. So let's look at the following experiment. This is an image of a water tank with a barrier that's placed right here, and water waves are generated to move vertically up like so. So the white line here is a wave front of those water waves. So this is a single water wave right here. And this is a highlight of the crest of the wave. You can see vaguely there's some more waves coming behind. So the wave was initially moving toward the top of the picture, as I showed, and is being reflected towards the right. So as you can see, the left end of the wave here hits the barrier, and then a wave or reflected wave is generated moving to the right. We see that the angle between the incident wave and the barrier is equal to that between the reflected wave and the barrier. So here, for simplicity, the barrier was placed in this square tank at 45 degrees. And since the wavefront is propagating parallel to the walls of the tank like so, the angle between the barrier and the wavefront will be 45 degrees. And looking at the image, we can determine, and of course this is measured experimentally as well, that the angle of reflection is 45 degrees as well. So here is a drawing of that experiment with the direction of the waves indicated with arrows before reflection and then after reflection. So you can clearly see that the angle of incidence and the angle of reflection are equal to each other. So the conclusion from doing experiments in reflection of light is that observing that light reflects from surfaces gives us no clues as to its nature. Both particles and waves obey the law of reflection. So we need to look at other phenomena associated with light to see if we can get an insight as to the nature of light. So the next phenomenon to look at is refraction of light. We learned a lot in the previous chapter about the behavior of light when it passes through boundaries between different transparent materials. Newton modeled light as being made of particles, and he thought that the particles of light experienced a force as they passed from air into a transparent material. So if you consider the incident light rays as being made of particles, according to Newton's theory, a force or downward force was acting on the particles as they entered the second material, which caused the particles to change the direction of motion, and thus the light ray bends towards the normal. So here we have a material with smaller index of refraction, such as air, and here we have a material with larger index of refraction, such as glass. So the transition here is from air into glass, and as we know from the previous chapter, when the transition happens from a material with less or smaller index of refraction into a material with larger index of refraction, the light ray will bend towards the normal in the second material. So according to Newton's theory, and from the observations that Newton performed in experiments, everything was matching. In Newton's model, when the particles would leave the second material, the glass, back into air, they would also experience this same force. And so because the force acts into the material, it now has the effect of bending the particles away from the normal. So once the particles leave the material, the effect of the force is reversed. So the force now is acting like so, which causes the particles to bend away from the normal. And this then matches the experimental results of light rays entering one material and then exiting the material. So this was a strong evidence, according to Newton, that the nature of light was particle-like. However, it turns out that waves also refract. So let's look at an experiment conduct it with water waves and see how they refract. So here again we have a water tank in which water waves are generated. And the water tank has two regions, a deep region and a shallow region. The boundary that runs diagonally across the photograph here, so this boundary, separates the shallow region on the left from the deeper region on the right. The numerical relationship between the angle of refraction and the angle of incidence is in agreement with the law of refraction. And this numerical relationship was given by Snell's law. Here there is an important difference between the wave and particle predictions. The speeds of the particles and waves do not change in the same way. According to Newton's model, when the particles of light enter the second medium, force is applied to the particles, which then implies that these particles will be moving faster in this material, in the second material. In the wave experiment here, exactly the opposite is true. Because the crests are continuous across the boundary, as you can see, we know that the frequency of the waves doesn't change. However, the wavelength does change. It is actually shorter in the shallow region to the left of the boundary. So you can sort of see, especially on the schematic drawing of the experiment here, how distance between two crests, which is the wavelength, is different in the deeper region compared to the distance between two crests in the shallow region. So the wavelength changes, but the frequency remains the same. But we know that there is a relationship between velocity of the wave, frequency of the wave, and the wavelength of the wave. And this relationship is V is equal to lambda f. Well, that means that the speed of the wave in the two different regions will be different. And more specifically, in the shallow region, since the wavelength is shorter and the frequency remains the same, then the speed of the wave will be smaller. So this experiment is equivalent to light traveling from a medium with smaller index of refraction into a medium with larger index of refraction. So if we imagine that this is this is air and this is glass, based on the discussion so far, it follows that light actually will slow down when it enters glass. According to Newton's model, it was the exact opposite. Light would speed up when it enters glass. So now here we have two contrasting models, and the only way to determine which of the two models is correct is to find experimentally what's the speed of light in glass when it comes in from a material with smaller index of refraction, such as air, for example. So experiments were conducted after Foucault found or determined the speed of light in air, and Albert Michelson improved on Foucault's measurements and found a ratio of 1.33 for the speed of light in vacuum to the speed of light in water. As we know from the previous chapter, 1.33 for water is the index of refraction of water. So that means that Michelson found a relationship between the index of refraction, the speed of light in vacuum, and the speed of light in a transparent material. And so the index of refraction n is equal to the ratio of the speed of light in vacuum and the speed of light in a transparent material. So the index of refraction of that material is equal to the ratio of the speed of light in vacuum and the speed of light in that material. From here, of course, if we have a material with known index of refraction, we can calculate what the speed of light in that material will be by simply dividing the speed of light in vacuum by the index of refraction. Well, it turns out that not only light changes speed when it enters from one transparent material into another transparent material, but also the different colors of light have slightly different speeds in that second transparent material. So the famous demonstration of dispersion of light, where white light is shown into a prism and then upon exit it separates into different colors, is the result of the fact that the different colors travel with different speeds inside the material of the prism, and so when they exit the prism, they get separated because of that. So now we have evidence that supports the theory that light behaves more like waves rather than particles. However, let's look at another phenomenon that waves experience, and let's see if light will follow suit. Interference of waves is the interaction of waves when they meet in the medium in which they propagate at the same place at the same time. We talked about that when I discussed waves on the rope. We talked about two waves that travel in opposite directions and how they superimpose on each other and interact with each other on the rope. An example of such interference was the standing waves that we discussed for stringed instruments and also wind instruments. Now let's look at the interference between waves created in water. So here is the setup. We have a water tank in which we have 2 point sources, those two dips, that are going to dip into the water with the same frequency at the same time, and will generate waves that will propagate in the water tank. Now, if we shine a light source above the tank and place a screen below the tank, we can then see the shadows of these water waves that are generated by the two sources and how they interact with each other, or in other words, interfere with each other, and we can then see what the interference pattern of those waves is. And so the image obtained on the screen looks like that. Here are the 2 point sources, and these are the waves that are created by the left source, the waves that are created by the right source. And as the waves meet each other in the water tank, they interfere with each other and create this pattern. Since the two sources are oscillating in synchron, so they're synchronous, then the pattern that's created in the water is essentially stationary, and so a drawing of this pattern looks like so. So here are the waves created by the left source, here are the waves created by the right source. We have the interference patterns shown right here. We have regions marked with these black lines where we have nodal lines, so cancellations of the waves. There is no oscillations along those lines. And then we have regions where we have antinodal lines. Those are the regions with maximum amplitudes of oscillation. And the central nodal line, the central antinodal line, is shown with red. So this pattern is essentially stationary in the water tank. And that is the interference pattern of these waves generated by the two sources. So, attempts to duplicate these results with two light bulbs, however, failed. If light is a wave phenomenon, it should exhibit such interference effects as well. Light from two sources does superimpose to form an interference pattern, but the pattern isn't stationary. Stationary patterns are produced only when the two sources have the same wavelength and a constant phase difference, meaning they produce the waves in unison with each other. So that is when the time interval between the emission of a crest from one source and the emission of a crest from the other source doesn't change. So again, the two sources are synchronous in their emissions. So because the phase difference between the light bulbs varies rapidly, the pattern blurs out and the region looks uniformly illuminated. Essentially, one could not discern an actual wave pattern like this, interference pattern. You simply just see a light spot. So after some experimentation, the first interference pattern of two light sources was demonstrated by Thomas Young in 1801. So here is a schematic representation of the experiment that Young conducted. So here we have a light source, and then we place a screen with a single slit in front of this light source. Now light is going to pass only through the slit, and then on the path of the light behind the first screen we place a second screen with two parallel slits of equal width and equal size. Now when the light passes through those two slits, we have two sources that have synchronous emissions of light. And then when we place a third screen on the path of the light, we see this pattern, which is an interference pattern. So Young let light from one pinhole impinge on two other pinholes or slits. Passing the light through the first pinhole produced light at the second pinholes that was reasonably in phase. The pattern shown right here consists of colored bars formed by light from the two slits interfering to form antinodal regions. So this is an actual image of the pattern generated on a screen. So the light source, of course, is white light, which contains all the colors. So once the light waves pass through those two slits, we have different amount of bending behind. And so when the waves interfere, they form these regions of different colors because, again, the different colors interact differently on the screen. And this is the interference pattern of white light. So these antinodal regions have large amplitudes and appear bright. So the regions where we have dark lines, these are the nodal regions where we have no light. And then the regions where we have bright light of different colors, these are the antinodal regions where the amplitudes are increased. So each color forms its own set of colored bars. Antinodal regions for the different rainbow colors superimposed to produce the colors we perceive. And now modern experiments of the same nature are in agreement with the wave model. So basically this is another confirmation that light behaves like waves. Another phenomenon that waves exhibit is diffraction. Diffraction is simply the properties of waves to bend around barriers. Because of diffraction, we are actually able to hear sound that's coming around the corner and see light that's coming around the corner. So imagine we have a corner like this, and then you have sound waves coming in from left to right. So if you are located right here, you know very well that you're going to hear the sound that's coming around the wall. Well, the reason for that is that once the sound waves reach this corner here, they will bend around. So they will, of course, propagate in all kinds of directions, but sound waves will bend around the corner, and that's how you can hear them. Same applies for light. Well, it turns out that This can be shown experimentally, again, with the water tank. So here we have a water tank, 3 different instances. We place a barrier with a small opening, with different sizes, of course, and then we generate straight water waves with straight fronts that propagate towards the barrier. And so when the waves pass through this small opening, the waves, due to diffraction, will bend around the corners. And then we start to see a pattern that forms behind the barrier that is not just a straight strip of traveling water waves, but it fans out behind the barrier. As we decrease the opening in the barrier, the pattern behind the barrier fans out more, and here, with even narrower opening, we see a pattern that is fanned out quite a lot. So, light waves exhibit the same property. Young's experiment points out another aspect of waves, which is the diffraction. And this is only possible because after passing through the 2 slits, light waves will bend, and then they will interfere with each other, and that's how they would form those light bands with different colors on the screen, right here. Now, if light was of particle-like nature, then performing an experiment like so would mean shooting streams of particles at the barrier, and then all you would see is only the particles that pass through the opening will continue behind the barrier, but they will be traveling still along straight lines. There will be no deflections to the side after the particles pass the opening. So diffraction of waves is another proof that light behaves like a wave-like object. Here is a set of photographs of diffraction patterns in the shadows of a razor blade and a penny. So, photographic paper was placed in the shadows of the razor blade and the penny. Red light was used from a laser because the light waves are in phase and can easily be made to approximate a point source. And as you can see, the edges of the shadows show the effects of the interference of diffracted light. And only a wave model for light can explain those effects. So you can see these effects right here in those regions, anywhere in between, and then for the penny around like that. Schematically, the image obtained for the diffraction of light for the penny is explained by this drawing. So we have light that is incident from the back side of the penny like so. And then the light rays reaching the edges of the penny will diffract, so they will bend around. And so when they reach each other or meet each other like so, they will interfere, and then they will form these interference patterns that we see in the actual image. Notice that we have a very bright center spot that is essentially the shadow here that is generated before the light rays interfere with each other. You can even observe diffraction effects of light if you look at the thin slit between 2 fingers. So if you bring the index finger and the middle finger together and place them in front of a light source and look at the slit between the two, you are going to notice a set of lines, much like the ones drawn here, which is a result of the diffraction of light rays through the slit and interference of the light rays to form this pattern. Through the discussion so far, we established that light is a wave phenomenon, but we know that waves can be either transverse or longitudinal. So then the question is light a transverse wave or a longitudinal wave? So we will determine this, whether light is a transverse wave or a longitudinal wave, by examining a property of transverse waves that does not exist for longitudinal waves, and then see whether light exhibits the same behavior. So transverse waves traveling along a horizontal rope can be generated so that the rope vibrates in the vertical direction and horizontal direction or any other direction in between. So we can determine a specific direction of vibration of the particles of the rope. So here is a drawing of the situation. Here is the rope, and waves are generated on the rope so that the rope oscillates vertically up and down, or the particles of the rope oscillate vertically up and down. So this wave is essentially vertical wave in the vertical plane. So if the vibrations generated on the rope are only in one direction, the wave is said to be polarized. Again, when the vibrations are only in one plane, the wave is polarized. So here, the vibrations are in the vertical plane, and therefore this wave is vertically polarized. The wave generated in the rope is vertically polarized. So this property becomes important when a wave enters a medium in which various directions of polarization are not treated the same. For instance, if the rope here passes through a board with a vertical slit cut in it, the wave will pass through the slit if the vibration is vertical, but it's not going to pass through a slit if the slit is horizontal. So the first board here has a vertical slit cut in it. Since the wave is also vertically polarized, it's going to pass through the slit. But now if we put another board on the way of the wave where the slit is cut horizontally, then the wave cannot pass through that slit. Then what happens if the slit is vertical, but the polarization of the wave is someplace between vertical and horizontal? So for example, we have our wave in this plane, which makes an angle that is not zero with the vertical plane. So the plane in which the wave is propagating is tilted from the vertical orientation by a certain angle. So you can imagine that you can represent the polarization of the wave by an arrow. For example, in the previous slide, we can use an arrow to represent the polarization as up and down along the direction of vibrations. So for a vertically polarized wave, the arrow that I will use is a vertical arrow. Then for our wave here, the polarization will be an arrow that lies in that plane here. But this can be presented as the sum of two arrows, one that is horizontal and one that is vertical. So essentially, I can represent the vibrations of this wave as the combined vibrations of two different waves. One that vibrates horizontally and one that vibrates vertically. So here are my two waves. We have the vertical component, which has vertical polarization, and we have the horizontal component, which has horizontal polarization. When you combine those two, the effect is this wave, which has a polarization which is at an angle with respect to the vertical or horizontal, however you want to say it. So then, if I place a board with a vertical slit on the way or on the path of this wave, what will pass through the slit is only the component that is vertical to the direction of propagation. So only this component of the wave will pass through the slit, and the horizontal component will get blocked. So that means that for waves that have more complex direction of their polarization. If we place a barrier on the way of the wave with a slit that only allows certain polarization to pass through, only that part of the polarized wave will pass through the slit, and the rest will be blocked. Determining whether light can be polarized is a little difficult because our eyes cannot tell whether light is polarized or not. However, nature provides us with materials that polarize light. The mere existence of polarized light demonstrates that light is a transverse wave. If it were longitudinal, it could not be polarized. We know that sound waves cannot be polarized because the oscillations of the particles of medium are parallel to the direction of propagation. So, commercially available light polarizing materials such as Polaroid filters consist of long, complex molecules whose long axes are parallel. These molecules pass light waves with polarizations perpendicular to their long axis, but absorb those parallel to it. Commonly used polarized materials are sunglasses. The effect of the polarizer is that it decreases the intensity of light that passes through sunglasses by killing some of the components of the polarized light. And this is very useful to decrease glare from light reflected from water surfaces or from snow. And if you haven't tried, grab a pair of polarized sunglasses and look at water surface, for example, lake. You will find out that with the polarized glasses on, it's much easier to see what's under the surface compared to without the polarized glasses. Because, again, the polarizers on the lenses kill some of the intensity of the reflected light. Another source of polarized light are computer screens and cell phone screens. And if you place a pair of polarized glasses in front of a cell phone screen and start to rotate the glasses, you will get to a point where the light from the screen doesn't pass through the glasses. This is because the light emitted by the cell phone screen is polarized in a certain direction. And so once you start to rotate the sunglasses, eventually the axis of polarization of the polarizer on the glasses will be perpendicular to the polarization of the light coming from the screen, which will then block it from passing through. Essentially, the effect is much similar to the effect explained here in this experiment. And so, through the discussion in this chapter, with various examples and experiments, historically it was determined that light behaves much like a series of waves. However, when modern physics was developed, it became clear that in certain instances, it is actually better to look at light as a series of particles, which then was able to explain certain phenomena that were unexplainable by considering light to be simply a wave phenomenon. So light, as other elementary particles, exhibits this dual nature of particle-wave depending on exactly what the application is and the context in which light or other elementary particles are discussed in. And with this, I conclude the lecture on a model for light.